Can today's processor architectures be more efficient? For years, processors focused on performance, and that performance had little accountability to anything else. Performance still matters, but now it must be accountable to power. If small gains in performance result in disproportionate power gains, designers may need to discard such improvement in favor of the more power-efficient ones. Although the current architecture undergoes a steady cadence, the performance and power improvement, additional gains are becoming harder to achieve. Everybody's going through and redoing their microarchitectures, seeing how they can improve them to a certain power. Sada Prakashi Madhuvapati, Product Marketing Manager, Director for Tensilica Audio Voice DSPs at Cadence. Many processor features intended to improve the computing throughput, such as out-of-order execution and a complex circuitry that raises power and circuit area. Similar improvement would right not be accepted today because of the power cost. So what opportunities remain with our current processor architectures? Efficient pre-implementation are not good enough. Many efforts to improve the efficiency involved better design of the existing architectures, and there are still some gain to be won there. When it comes to implementation, there are a lot of power-saving techniques, such as market twinning, tracker of the marketing, and others. Our very basic approaches leverage the process improvement to do more with the less power. More slow isn't that, Swinen said. We are still getting smaller process technologies, and there's always been the number one way to reduce power. It will run out soon, but it's not quite there yet. This also can drive process decisions. When you choose a certain process node, you need to have the power efficiency in mind as well, said Madhuvapati. 22 nanometer is basically 28 nanometer with a much better energy profile. He noted that a 12 nanometer with another popular node for power efficient designs. 3DIs provide a new power point somewhere between a monolithic die and a PCB level assembly. A 3D IC is going to higher power than a monolithic chip, but a 3D IC has much more power, high-speed implementation than available through the multiple chips connected through the traditional PCB traces. Noted Sweden. Co-packaged optic CPU bring optics closer to silicon, and that does also can reduce power, but it's been a long time coming. CPU has been around for a long time, but it's been economically very difficult to justify the technological complexity, and trade-offs in the end were not necessarily favorable. Explained Swinen. That seems to be shifting, especially that a technology gotten better, and partially, and the need for high-speed digital communication has grown so intense that people are willing to pay more for it. Nano techniques are practical. Some implementation techniques sound interesting but bring their own challenges. Asynchronous design is one of them. One on the plus side, every register talks as quickly the next one as it possibly can. Explained Swinen. There is no central clock. No, the whole clock architecture goes away. You don't have a slack where one data path is waiting for some other data path. It's been around for many cases, but it has failed to break through except in specification cases. Because the performance is unpredictable, I guess in a game what that timing is going to be. The very Every chip can be slightly different because of process variability. It's also not clear that it really saved power in the end. The self-timing handshake means that the flip-flops have to be much more than complicated. Sweeney said, when you net it all out, all flip-flops use more power, and the question remains, does it really end up saving you much power for all this complication and lack of predictability? And the net of it has been that hasn't really taken off as a design methodology. Spurious power of glitch powers can be tend to reduce power using data and clock gating. It will add area, but the effect on a spurious power can be pretty large. So Mathivapati. This requires analysis to identify the primary contributors. Not only does it measure the glitch power, but it can also identify what is causing this glitch, noted Sweden. In the end, one can have only one much impact at the implementation level. There is a limit to how far you can go with the RTL, which is ironic because most of power saving opportunities are at the RTL level. So Sweden, the biggest benefit really is at the architectural level. Expansive features. Artificial intelligence AI computing has pushed the design teams up against the memory wall. So given the industry focused on AI training and inference, a huge amount of attention has gone to putting trillion of parameters when they need to be there without burning down the house. But the processors themselves also burn energy, and other workloads will show a different balance between the execution power and data movement power. Although the clock frequencies continue to climb gradually, such changes really are not fueling performance gain as much as they once might have. The real target of improvement has been trying to keep as much of the processors busy as possible. Three architectural features can illustrate the complex changes made of such gain. Speculative execution, also known as branch prediction, out-of-order execution, and limited parallelism. The purpose of speculative execution is to avoid a situation where one enter a branch instruction must wait the outcome before deciding which branches to follow. Waiting until that point will delay the result until the system fetches the instruction that the branch result dedicated, potentially all the way from the DRAM. Instead of one branch is followed subsequently, speculatively, hopefully the most likely branch. Usually completion of the branch decision will validate the decision, but sometimes it won't. At the time, the one must back out of the speculative calculation and start the other branch, including the potential instruction fetch from DRAM. Branch predictions typically accompany out-of-order execution, a feature that allows some instructions to be executed in order different from how they appear in the program. The idea is that the instruction may store awaiting data while another later instruction is ready now, but that the later instruction can't depending on the earlier. But one main of the limitation of the serial programming paradigm is that instruction must be listed in order. Even if they don't depend on each other. So out of the order execution is a complex system that can start multiple instructions ahead of time, ensuring that the original program semantics are honored. Figure 1. Intel processor microarchitecture example. These are particularly unique include out-of-order processing because of the need for backward code compatibility. Instructions are first converted to the microcode before execution. This model has 11 function units and 8 for execution and 3 for data load and stores. Area versus performance. These are not simple systems, and they may come with a price disproportionate to their benefit depending on how they are built. For example, a branch predictor keeps a list of prior branches taken, said Lars Klein, program director, high-level synthesis division at Siemens DDA. And like a cache, that list often uses the bottom end bit of the branch target as a hash key into the list of branches taken. So n could be 4 or 16 or more, and the number of entries in the list could be 1 or 2 or 32. You can store the full target branch address, or maybe the only bottom 12 or 16 bits. A bigger and more detailed memory of what branches were taken results in the better performance, but obviously takes more space and power. The region benefit can vary. According to a small simple branch predictor might speed up a processor by 12%, whereas a large complex one could improve the performance by 30%, but it might be 10 times larger or more than a small simple one. Is Klein example. Klein explained. In terms of area, who cares? But for power, it does become a big deal. Cadence improved the performance of some codecs by restructuring them. Elder code with some few branches, we are seeing performance improved by about 5 to 15%, said Mahabhati. The number of branches in codecs is less than 5%, and almost none in the inner execution loops where we use ZOL, zero overhead looping. More generally, the company finds more branches in typical programs. Code in the wild has about 12% instructions that are branches. Mahabhati. Each of these represents an opportunity to speculative execution. Performance gains can be as 30% or higher, as the average instruction executed per cycle goes up significantly. Even if the half of the prediction is successful, combined overhead, branch prediction, and out-of-order execution may be in a 12% and 30% range. Klein recalled the Clever founder Anand Agrawal discussing a kill rule. What the kill rule stated was, if you're gonna to put a feature into your CPU, it's gonna increase the area, and if the increase in the area is greater than the increase in the performance that you get, and you do not add the feature, he said. Parallel computing is an easy answer. Parallelism clearly provides another means to higher performance, but what's available in the current processor is limited. There are two ways of today's mainstream processor provide parallelism. By instantiating the multiple cores and those multiple functions units within a core. A function unit that would have been a simple arithmetic logic unit, ALU, in the past. It's what executes the actual instruction. A given function unit will typically be able to execute some number of instructions beyond simple math. They also may include multiplier, dividers, address generations, and even branchings. By providing multiple such units, when one is busy, another may be available to work on a different instruction, which may be out of order. Different processors have different numbers of function units, and code profiling helps to determine the mix and distribution of instructions supporting them. This helps parallelize instruction execution where possible, but the processor overhead, such as instruction fetch, happens serially. Surely, parallelizing the computation is one of the best opportunities for improved performance and with a less treated out processor. It could be more powerful efficient, but such a solution is new. Many core processors were commercially available more than a decade ago and failed to get a traction. Few algorithms are fully parallelizable. Those are usually called embracing parallel. Everything else has a mixed parallelizing code and a segment that must serially. Amdahl's law identifies those serial portions as the ultimate limiter. Some programs can be highly parallelized, others not. But even when an algorithm doesn't appear parallel, other opportunities might exist. Fractal setting is an example. Your f of x is f of x minus 1. Explain decline. Each pixel is individually computed through a long serial chain. But if you're doing an image, you've got a 1024 by 1024 or whatever the image size is. So you've got a lot of opportunities for parallelism by computing multiple pixels at the same time. Processors that a data center serves, they come with as many as 100 or so cores. But unlike the many core processors before, they are not used for a single program. They allow the execution of multiple programs for different users requiring cloud computing. The problems with parallel, even if they get parallelized, the catch is the processor must be programmed in parallel. That typically has meant explicitly managing the parallel nature of the code. For instance, by invoking the pthreads. This is much fuzzier than a typical programming, requiring a knowledge of data dependencies to ensure that in-order semantics are met. Although some tools have existed for helping with this, none have entered mainstream software development. In addition, manually managing the parallelism may require different programs for different processors. Programs may run may not be optimal if more threads are necessary than a given processor can manage in hardware. Going to software parallelism may hurt performance owing to context switching overhead. The biggest problem is that software developers have turned up their noses at explicit parallel programming. There is a strong desire that anything new be programmable using current methodologies. Software guys have soundly rejected the notion of a 100 core processor except one area that we're seeing the start creeping in the GPU and TPU, Klein observed. This is why the many core processors fail commercially. Even so, parallelization is primarily about performance. Getting the power down requires a modest core and an aggressive power down strategy so that either cores aren't consuming energy. Parallelism also helps restore overall performance that might have been lost when making a core more efficient. My argument would be the array of the really simple CPUs is the way to go, but it does require a change in a programming methodology, he said. The only that I've got for that happening is also I have to be able to create a parallelizing compiler, which is something we as an industry have never been able to do. The practical way that we have today to deal with algorithms that bog down on a general purpose processor is employ accelerators as shown in the blocking offload so that the accelerator can handle it efficiently while the CPU does something else or sleeps. Accelerators can broad or narrow. Accelerators of types have existed for decades. Too much the most attention is devoted to those accelerators that can speed up the training and inference given the very specific intense computation required. But such accelerators aren't new. Heterogeneous computing combined process cores provide optimizing power and performance, said Paul Karajuba, Vice President of Marketing at Expedera. This obviously includes NPUs. NPUs address all AI processing from less efficient CPU and GPUs. However, not all NPUs are created equal, not only in approach, but also in architecture and utilization. This is because the accelerators may be highly specific, even customized, while others will remain more general purpose. If the AI workload is well known and stable, a custom NPU can be delivered significant gains in power and cost efficiency. Karajuba continued. If you need a flexibility to support multiple models or future AI trends, a general-purpose NPU is more adaptable and easier to integrate with the existing software ecosystems. So the customizing accelerator will tune in more specifically to each workload, and the effort should improve the power efficiency. A way to increase the efficiency, the power processor subsystem, specific NPUs is create a more application-focused NPU rather than employ a more general-purpose one, said Karajuba. Custom NPUs often use specialized MAC arrays and execution pipelines that may tune for a specific data type and model structure. General-purpose NPUs comprise configurable compute elements that support multiple data types and a typical address a broader range of layers and operators. Jettisoning features that aren't necessary for a given task can yield significant leisure. In real-world applications, expect a typical siege to 3 to 4 times gains in processor efficiency, measured in a top SWN2 more than 2 times gains in utilization at defined edge actual throughput, theoretically maximum throughput when a custom NPU is deployed. What happened when we run out of the tricks? There clearly remained a winning opportunity for making the processors and the process subsystems more efficient. But at the same time, in the not too distant futures, we risk running out of days. What happens then? This is where new processor architectures might prove helpful, such changes in trivial. However, given the massive ecosystem that underline current architectures, fortunately, there are some new architectural ideas as well as the possibility of giving us some generality. Okay, today I read this article that can today's processor architecture be more efficient. Thank you for your time. See you next time.